Okay, so physics practicals, and now we are moving towards next practical, and the name of the practical is laser. Okay, do you remember the full form of laser? LASER, full form of laser. L stands for light. Okay, out of laser, L stands for light, A stands for amplification, S stands for stimulated, E stands for emission, and R stands for radiation. Okay, that is light amplification by stimulated emission of radiation. So this is the long form of laser, and today we are going to discuss a property of a laser, that is they have to measure a property of a laser, and that property is nothing but the wavelength. Okay, you might be remembering the definition of wavelength. It is the sum of crest, the distance of some crest and trough, or it is the distance between two particles which are in the same phase in case of waves. And we are discussing about laser and its waves. And also, you know very well that laser waves or light waves are the electromagnetic waves. Okay, and therefore in this experiment, this is the experiment from second group or B group. Okay, and apparatus required for this experiment are laser source. Okay, as shown in this diagram, this is laser source, then plane diffraction grating and the scale, etc. Okay, so in paper second, in optics and laser paper, you have studied everything about laser source, production of laser, types of laser, its population, inversion, Einstein's coefficients. Okay, pumping, optical pumping, mechanical, and after that electrical pumping, ruby laser, helium neon laser, properties of laser, applications of laser, etc., etc., from Kamunde madam. And after that, I have discussed with you the properties of plane diffraction grating. Initially, what is diffraction? Okay, and after that, plane diffraction grating. So in this case, if you move towards the ray diagram of this experiment, the first component of the ray diagram from the left hand side is the laser source. Okay, always you write laser like this, that is capital LASER, all caps. Then second one is the diffraction grating, and you're observing that this light, that is a red light, purposefully I have drawn red color because this is the ruby laser. Okay, and the color of ruby is red. Okay, wherever you come in the practical lab, in the physics practical lab, you will observe that the ruby laser is having red light, and therefore red light is coming from the laser source. You will observe in the laboratory. If any obstruction or any obstacle that is in the form of grating is kept between the path of laser and the screen, here is the screen, we can observe that due to diffraction of the laser light or the diffraction of the beam, laser beam, the lights, that is the rays of laser are getting diffracted. So here another phenomenon is observed, that is a diffraction of laser light. Okay, and the diffracted angle is the theta with respect to the original direction of beam. Okay, so at the center, suppose if diffraction grating is absent, then this ray, it would continue the path at this particular point. Okay, suppose if diffraction grating is absent. Okay, suppose this diffraction grating is absent, then the laser beam, it would continue the journey towards screen, and it will collide the screen at this particular point. Therefore this particular point is bright point, and it is, according to our diffraction theory, it is to be known as central maximum. Okay, and for that central maximum, the condition is there, that is order of diffraction, that is small n is equal to 0. Okay, so inside the bracket we should write n is equal to 0. Actually this is n is equal to 0. Okay, so this is order of diffraction is equal to 0. Order of diffraction is 0 means no diffraction is there, since the diffraction grating is absent. Now the moment when you insert the diffraction grating between the path of laser beam and the screen, you can observe that number of spots are visible. Okay, so depending upon the angle of diffraction, the intensity of the laser beam is getting diffracted along with the light. Okay, so here if you observe first order, that is for n is equal to 1, that is bright spot after central maximum, that would be first order maximum. Then above that n is equal to 2, that is second order maximum. And below central maximum n is equal to 1. Okay, again first order maximum. And at n equal to 2, again second order maximum. Okay, so the order of diffraction depends on theta and the distance between these two. Okay, you have to find out the distance, that is this xm. The distance between these two, this distance x suffix m, or this is also x suffix m. This distance, whatever length of this arrow is there, the arrow or the length of the arrow is the distance between these two bright spots. Okay, suppose you want to measure the distance between this central maximum and the first order maximum, then the length between these two is, say for example, suppose this capital D is equal to 20 centimeter. Okay, I am giving you example. Suppose capital D is equal to 20 centimeter. What is D? D, according to this diagram, ray diagram, D is the distance between screen and diffraction grating. Okay, capital D is equal to distance between screen and diffraction grating, and small distance, that is xm, capital X suffix m, is equal to, this is the distance between the central maximum and the first order maximum. Okay, so you have to find out the distance between central maximum and first order maximum. In, you can write the value in first column, and after that in second column you can write the distance between central maximum and second order maximum. Okay, so this can be obtained with the help of the scale which is fixed on the screen. Okay, and after that you have to vary this D, and ultimately because of variation in D you will observe the variation in this distance of xm. Okay, so this is the experiment and this is the ray diagram regarding the laser experiment. Okay, so in this case in this experiment you have to find out wavelength of the laser beam. This is very simple experiment. Okay, and with this arrangement and only two readings, we have a formula to find out wavelength of the laser. So here is the actual three-dimensional experimental setup to determine wavelength of the laser. Okay, so here once again we have a laser pointer which throws light towards diffraction grating, and there is a holder. Here we have targeted laser beam on diffraction grating, and to hold diffraction grating we have a frame, and that frame is known as a target holder. Okay, so because of the diffraction, do you remember the order of diffraction? Order of diffraction small e, or it is also denoted as D, is equal to 1.69. Of course, if you remember, 1.69 into 10 raised to minus 4 centimeter. Okay, so this order can be obtained as, if you take the ratio of 2.54 centimeters, okay, divided by 15,000 lines. per inch. Okay, LPI, if you remember. So if you divide 2.54 centimeter by 15,000, you will get this value. Okay, so this is the grating element. So just imagine that if this is 10 raised to minus 4 centimeter, centi itself stands for 10 raised to minus 2. Okay, so 10 raised to minus 2 and 10 raised to minus 4. So 10 raised to minus 2 centi, 10 raised to minus 2 and 10 raised to minus 4 combinedly 10 raised to minus 6. So the grating element is of the order of 1.69 micrometers. Okay. So due to such a small gap between the two ruled lines, the laser beam is getting diffracted. Okay. So as you compare the thickness of the laser beam over here before diffraction and after diffraction. Okay, so this is the diffraction. Now you have to find out the distance, that is capital D, which is the distance or the length between diffraction grating and the screen. Okay, and because of the grating element, that is 1.69 into 10 raised to minus 4 centimeter, because of the grating, laser beam is getting diffracted, and that can be recorded on the screen. Okay, so here depending upon the order of diffraction, capital D, okay, order of diffraction n, then diffracting angle theta, capital D, we can observe or we can find out the distance between the central maximum, this one according to this diagram, and the first order maximum. So here this is also known as y1 and this is also known as y2. Okay, so here we have denoted that one in terms of xm. Okay, so here, if you observe the same experiment in the laboratory, you can observe that whatever is pattern on the screen, that pattern is visible to you on the screen. Okay, this experiment is to be carried out in the dark room. Okay, so in the dark room, at the center, this is the central maximum. So here n is equal to 0, then this is n is equal to 1, this is also 1 on the either side, then this is n is equal to 2, this is also n is equal to 2, this is 3. Okay, this is 4, n is equal to 4, and n is equal to 5, this is also n is equal to 5. So I am writing the order of diffraction. Okay, so depending upon the angle of diffraction, you will find out order of diffraction up to n is equal to n. Okay, depending upon the grating element. So such type of pattern you can observe in the laboratory, or depending upon the clarity of grating, you will observe that this pattern where n is equal to 0, okay, n is equal to 1, this is also 1, then this is 2, this is 2, then next one 3, then 3. Okay, so similarly here also we can observe the n is equal to 0. So you have to adjust the grating, plane of the grating in such a way that you will observe such type of pattern as shown in the first strip or first diagram. Okay, so depending upon the plane of the grating and the laser which is striking on the diffraction grating, you will find out such type of pattern. So you have to make an attempt to have such type of pattern. Okay, so don't go for such pattern and don't take the readings. Okay, so this type of pattern, that is prominent, n is equal to 1 to n is equal to minimum 6. Okay, n is equal to 1 2 3 4 5 6 dark circles or spots of the laser beam are visible on the screen. Okay, so after that, here depending upon the intensity, the same pattern is shown in this diagram. Okay, so for your easy understanding, if we consider this as central maximum n is equal to 0, On the right hand side of my screen, it would be denoted as +1, +2, +3, +4, +5, and +6. Okay, for the right hand side, and for left, -1, -2, -3, -4, -5, and -6. Okay, so whatever you observe is this only spots. Okay, on the screen, and here you can denote it. Okay, this is obvious according to this ray diagram also. Okay, so after this ray diagram and the spot procedure is very simple, as I explained you. Arrange the laser source, grating, and the screen as shown in the figure. Obtain the steady diffraction pattern on the screen. Okay, this is such type of steady diffraction pattern to adjust and observe. Okay, measure the distance between grating and screen D, capital D. Measure the distance of M is equal to 1. Okay, then also which is central maximum, that is x1. Then also measure distance of m2, that is for second spot, second order maxima with the central maximum x2. Calculate wavelength lambda of laser source using the formula. So here lambda is equal to, this is formula, lambda is equal to d divided by m into xm upon root xm square plus d square, where d is the grating element. Okay, so xm is distance of mth order from central maximum, m is order of spectrum, and d is the distance between screen and grating. So here, suppose initially the d is 6 centimeter. Okay, so you will, this is an example, don't take such readings. If d is equal to 6 centimeter, then xm would be 1.4 centimeter, and for first order, and xm for second order it would be 2.1 centimeter. Okay, if you increase the distance capital D further, if it is say for example 10 centimeter, then this first order it would be 2.9. This is example. Okay, and the second order would be 3.6. Okay, so how, this is the course how it varies. And after that, just you have to substitute the d values here, then xm values for first order and second order respectively. Then this d is present over here, then the m is equal to 1 or 2. Okay, because we are taking the readings for first order and second order, so m would vary depending upon the reading. And just you substitute the xm values and d values, you will able to find out the value of wavelength of the laser beam. So suppose if you take 8 readings, that is 1 2 3 4 into 2, 2 readings for each observation, you will have 8 calculations of wavelength. And just take a mean value of wavelength, you will find out the wavelength of laser beam is equal to something. It would be 69, it would be around 6900, okay, angstrom units. So you might be remembering the wavelength of laser beam according to our laser chapter. So this is all about the laser experiment. Okay, so after that we have to discuss another experiment, that is second experiment. Please wait for a second. We have another experiment. And the name of second experiment is Photocell. Okay, you have studied Photocell and the photoelectric effect in HSC. This is also the experiment from group B. Okay, so here we have to verify the inverse square law, which is there in the classical mechanics or in the Newtonian mechanics. And with the help of this photocell, we have to plot the polar graph of intensity distribution for the filament of the bulb. Okay, so once again, I shall read the aim of this experiment to verify inverse square law, okay, which is also present in the Newton's law of gravitation, okay, that is 1 upon d square law, okay. D is the distance between two objects, okay. So this is inverse square law. 1 upon d is inverse, and also square of d and 1 upon d square, okay, which is inverse square law. And this law you have to verify with the help of this photocell. If you remember the Newton's law of gravitation, you will come to know how the inverse square law is defined, okay. So here we have to use photocell to verify this law, Newton's law or inverse square law, with the help of polar graph and its intensity distribution, which is obtained for the filament of the bulb. Okay, so here apparatus required are photocell, filament bulb, battery, illuminator, micrometer, scale, etc. So first I shall read the procedure. Make the connections as shown in the circuit diagram. Initially, keep the light emitting filament very close to the bulb, that is nearly equal to 10 to 15 centimeter to the photocell, and adjust the angular position of the bulb to get the maximum current in the circuit, okay, which is recorded in the milliammeter, milli or micrometer depending upon the intensity of the photocell. Note this current I and the distance small d between the photocell and filament bulb. Take 8 observations by increasing distance small d. In earlier experiment, we had capital D, okay, and here notation is small d, distance, okay, and note corresponding current I. Finally, verify the inverse square law by plotting the graph of current versus 1 upon d square. So here you have to vary increase in the distance, that is small d, and you have to note down current I, okay, in the micrometer. So this is the actual photograph of the photocell experiment. So here this is the photocell having emitter and collector, okay. So in the form of the cathode plate which is inside, this is the glass bulb, okay, or glass envelope, and inside the glass envelope the silver colored is the cathode, okay, that is C, and opposite to that is the collector, that is anode. So here this cathode, in this case of photocell, this cathode works as an emitter and the anode works as the collector. Suppose white light, that is visible light, is incident on the cathode ray. So because of the photoelectric effect, you might be remembering the photoelectric effect which was investigated by Einstein. So due to this phenomenon of photoelectric effect, if we supply battery to the cathode and the anode of the photocell, we can observe the current, okay, which is shown in the micrometer. We can observe the current depending upon the distance between the source of light and the photocell, okay. So here you have to measure small d, that is the distance between photocell and the source of light. Suppose source is somewhere here, source, distance between source of light and photocell, and just note down the current in microampere, okay. So after this experimental arrangement, we have the circuit diagram. So according to this diagram, this is the photocell, okay. This photocell consists of a cathode K and the anode, okay. This is the three-dimensional diagram, and just this is the top view of the diagram. So small d is the distance between the photocell and the lamp. Then this is the plug key and the micro ammeter having specific range which are connected in series with the photocell. So due to rays reaching towards cathode and then anode, photoelectric effect is observed, and the flow of electrons or the flow of charge passing through microammeter are noted as current, that is correctly photoelectric current. Okay, and due to photoelectric effect, so we are observing actually photoelectric current due to photoelectric effect over here which is taking place inside the photocell. So here in this case, only two readings are needed. Two readings means eight number of observations, 8 to 10 number of observations, and only two readings, that is D and I. Okay. So after that, first is measure D. Suppose initially D is 10 centimeter, and if current is 450 micro ampere, if you increase the distance D further by 2 centimeter, it would decrease. Suppose it is 430 micrometer, then it is 10, small d is 10, 12, 14, 16, and so on. It would decrease depending upon the intensity of the light. Okay, then this is d, then square of d. Okay, that is d square, then inverse of the values obtained in this column, then I into d square. Whenever and wherever needed, you will take this value. Okay, you can have the multiplication between I and d square if required in the examination. Okay, and this is 1 upon d square. This is not I, this is 1. Okay, note that this is 1 upon d square. Okay, because according to observation table we have to verify the inverse square law. This is 1 upon d square, therefore unit is centimeter raised to minus 2, and this is I into d square, micro ampere into centimeter square. Okay, so just to clarify, this is 1 and this is I. Okay, slight difference is there between these two. And now the most interesting thing is the graph. If you plot a graph of I on the y-axis and 1 upon d square on the x-axis, you will find the straight line which is passing through origin. Okay, and after these readings and the graph, you will conclude that as the graph of current versus 1 upon d square is a straight line. Therefore, you can conclude that intensity of light, which is a measure of current, is inversely proportional to square of the distance. Okay, which verifies the inverse square law. Therefore, result is as the graph of I versus 1 upon d square is a straight line, inverse square law is verified. So here in this experiment, just you have to take the readings of d and I. Just you have to observe what is going on there. Okay, and just take square, then inverse and plot a graph. So this is the experiment requiring only 15 to 20 minutes, and earlier one laser needs only half an hour. Okay, so within 1 hour you can conclude these two experiments. So after that, this is all about experiment. After this experiment, another important information is there about the inverse square law. So here, inverse means reciprocal, square means you know very well what is square, and this is inverse square law. So according to this inverse square law, this type of information is always asked to you in oral examination of the practicals. Okay, so in science, an inverse square law is any scientific law stating that the specified physical quantity means here we are comparing intensity of light with the square of the distance. Okay, so here light is the physical quantity in our experiment. So here specified physical quantity is inversely proportional to the square of the distance, okay, from the source of that physical quantity. So according to this experiment, the statement is obvious. Next, the fundamental cause for this can be understood as geometric dilution corresponding to point source radiation in three-dimensional space. Okay. Second, the example is suppose radar energy expands during both the signal transmission and the reflected return. So the inverse square for both paths means that the radar will receive energy according to the inverse fourth power of the range. Okay. Next, to prevent dilution of energy while propagating a signal, certain methods can be used such as waveguides, which acts like a canal does for water, or how a gun barrel restricts hot gas expansion to one dimension in order to prevent a loss of energy transferred to a bullet. Okay, so these two are the examples how to prevent loss of energy. In case of light, we have waveguide. In case of gun, we have dimensional barrel. Okay. So here is the diagram how this inverse square law works. Suppose this is the source at particular point, and now A is the area for which you are observing certain amount of intensity, which is measured in lux. Okay, lux is the unit of intensity. Okay, observed for a particular area. Lux meter is there. Now, after this particular distance, that is for small r, we have certain value of intensity. Okay. After that distance, if you further extend the same distance, that is 2r, suppose this is 10 meter from the source, that is the distance between source to r is 10 meter. Now if it is increased to 20 meter, okay, now the cone or the area due to wavefront of the light, we can observe that this area is traveling towards this. Okay, and because of that, if we take every rays on the wavefront, we can observe that this intensity, suppose here in this area 1 2 3 4 5 6 7 8 9 rays are there, but here for this particular area we have only 1 2 and 3 rays. Okay, it means the intensity in this case for this particular area has decreased, which is the function of distance. Suppose further if we increase the distance by 30 meter, then for the same area, we have only single ray passing through that area. So this is how inverse square law works. It means with respect to inverse of the square of the distance, light intensity of that particular source decreases. Okay. And again, this is possible in case of light, which is related to our experiment, light and other electromagnetic radiation. The intensity, which is very important for you, the intensity or illuminance or irradiance of light or other linear waves radiating from a point source, which is defined as energy per unit area perpendicular to the source is inversely proportional to the square of the distance from the source. So an object of the same size twice as far away receives only 1/4 of the energy. 1/4 means 1/4 of the energy. Okay, in the same time period. So it receives only 1/4 of the energy, and which is obvious. So this is nothing but the inverse square law. So in this case also, the dark or shaded area is the intensity in case of electromagnetic radiation. Okay, so at this particular point, suppose once again we can take 10 meter, then 20 meter, and then 30 meter. So from 30 meter distance with respect to source of light, that particular area, suppose 1 feet by 1 feet, that particular area is receiving smaller or lesser amount of intensity of light. So which is explained as intensity is equal to A divided by 1 square, A divided by 2 square, E divided by 3 square, and so on. Okay. So this is all about the inverse square law, which is needed for you to understand this photocell experiment. Okay. So this is all about photocell experiment. So today we had discussed two experiments. First one is the photocell, laser, that is wavelength of laser, and the second one is the photocell. Okay. So after that, we shall discuss next experiment in the next lecture. Okay. So if you have any doubts, you can ask me